Okay, now the next presentation is a little different than the usuals, because I want you to, when I'm presenting, think about everything that was said today. Because before that, I need to acknowledge that this work was done under the guidance of Dr. Shakir Shatnawi, Jorge, and Katia, which is an engineer. And what we're trying to address here is the concept of how can we use, or should we use, or asphalt rubber in new pavement construction. And basically, I think we need to look at everything we know and give a step forward. Think about what has happened with the bridges, for instance. The Romans did bridges. They had stones, they had these arches, and you had a design method adapted to the material you use. Then we invented concrete, and our bridges have been designed taking in consideration the material we have. Then Eiffel and many start making steel bridges and Eiffel Towers, and they have the design adapted to taking maximum performance from the material. Then they invented reinforced steels, and we have the reinforced method in the curves of the rebars, and we have moved forward because now we have a new material, we have adapted design. Then we have the cable bridge, now the Golden Gate and many other stay cables, because they have now these super fantastic steels and epoxy coatings, and you can take advantage of that design. Now, I think this is time to start thinking if the designs we are using now in our normal construction are really addressing the capabilities that we now have in the materials. Now, we have gap grade, open grade SAMI, and we have been using them, and we have design guides, but are we really taking advantage of these materials? Do we have an adopted reflective design method to take advantage of the materials? Clearly, we don't, and I'm going to demonstrate. How can we take advantage of the extra durability of these materials? How do we incorporate in our designs the fact that a SAMI does really waterproof the pavement and water does not go in, and we don't have as much a weak effect of having the moisture in our pavement? How do we incorporate all that? Are we missing the boat here? Shall we start thinking outside the box? So we know, and has been well reported, that SAMIs, like Dr. Shatnawi said, they work great. Now, how do we incorporate this work great in our knowledge? How can we push the limits? Now, and how can we incorporate also the limits that are given to us by these two gap-graded and asphalt rubber mixes? Arizona started doing some tests many years ago, and they tried new concepts to resist reflective cracking by putting asphalt friction courses, then a SAMI, then asphalt friction courses, trying to make it waterproof, trying to make crack resistance, and they actually did finite element analysis at the time. And look at this. They realized that the stress at the crack tip with SAMI and no SAMI was tremendously different. But, we have this map, we look at it, it's different, that's okay, and then we'll go home. How do we incorporate this knowledge in our designs? Now, later came work that George Pai and I and George Way did for RPA, and we're trying again to incorporate the reflective cracking design mechanism into a normal practice. And we get good correlations, and the model correlates very well. Don't worry, the important part here is to know that there are tools. And the tools seem to indicate to us that reflective cracking is the method, is the key aspect that must be controlled in overlays. Okay? Why don't we think that a new pavement is all cracked, make a pavement all cracked, and control the reflective cracking? Now, this is a new, different way of thinking. What we do so far is we control the stress on the top of the subgrade layer. We control the stress on the bottom of the asphalt rubber, like the Asphalt Institute teaches us to do when shell method. But if we have this material that is so good at resisting reflective cracking, why don't we control that stress? You'll see where I'm going with this. Now, through that method, we have developed a method to control reflective cracking and relate overlay thickness with the number of easels that a certain traffic can, that a certain pavement can take, a function of the pavement conditions, layers, moduli, and interestingly, the model tells us that asphalt rubber layers can take less thickness for a given traffic. Now, remember when I made this comment this morning regarding ALF? I think this ALF study is a fantastic basis to start thinking all new about designing pavements. We know, it is reported, that we had at least these two materials, conventional and asphalt rubber, and it was reported that one did not crack and the other cracked. Now, first, I want you to think that the difference in price in these two materials is not tremendously. I made an analysis for China, and if you design a pavement with this traffic, it costs maybe 20 RMB. RMB is the unit, forget, $20, let's say, for 1,000 trucks. If you use this structure based in this graph, you basically take the same amount of traffic with $2. It's a 10-to-1 difference. Now, when we have a pavement like this, they all alike, this one is lasting so much long and this one doesn't. Now, can we predict this? Can we design this? This is a new pavement. Why don't we make all new pavements like this? We're saving tremendous amounts of money. Well, we know that this lane did not crack, that one all cracked, so this lane on the bottom is cracked, that's not cracked, the cracks don't come through. Now, what we do now is we control the crack on the bottom of that layer, we control the crack on the bottom of that layer, and the base here and the base here. So, based on our current design methodology, this pavement is no good, because on top of it, that layer there is softer. So, from all methods of designing pavements today, this thing is going to crack and fail before that one. But the reality is absolutely the opposite. Now, we took the time, and FHW is very gracious and sent us all the FWD data, all the data that they could, and we did the analysis, back analysis, and we calculated the moduli of all the layers, and using shell, and this can be done use Asphalt Institute or using any normal use, but shell worked well. We predicted, using the data that they send us, we predicted that the different sections, well, there's some variability. Some would fail after 22 cycles, some 35 cycles, and for 10% cracks, the reality is that it failed in 30,000 cycles. So this is this section. We were able today to predict how this section behaved. Very well. So meaning, up to today, researchers, engineers particularly have done a good job. The models we have can predict what happened at ALF. Now, the same models tell us that the asphalt rubber section should have failed after 8,000, 23, 12,000, 22,000 cycles. The same models tell us that. But the reality is, after 300,000, it didn't fail. We could ride that surface, it's a beautiful surface. If the whole roads was like that, we'd have no cracks. So, we need to go back and rethink how we do pavement design, because we want that performance. Why are we going to bury more money? We want that performance. Now, here is just an idea how we can get there, but using the overlay design method that was done for RPA, we can imagine that there's an overlay, the pavement, as you just, so we don't lose you for a second here, remember there are 2 layers here, and actually that pavement was made in 2 layers too. So these 2 layers, let's imagine that this is all cracked, and now how long does that one take to resist life, like that one, resist cracking? So here we can see that one would fail in about 15,000 or 20,000, no, 10,000, well, 15,000 passes, like the conventional mix here. But asphalt rubber, for those conditions that were provided us by FHWA, would fail after, maybe 100,000 cycles. Now we have models that indicate already that we could make those pavements last longer. So, interestingly, if now we know that those 5 centimeters of asphalt rubber would make the pavement last that long, we can now go to the model and see that the thickness of equivalent asphalt, if it wasn't asphalt rubber, would be asphalt, how much would be? And turn out 18. And this one, for the exact cycles, let's imagine that this went 300 cycles and 301. Everything was cracked. So the equivalence in that case would be to 15 centimeters. So, in fact, asphalt rubber, the tests done by FHWA indicate that as a minimum, imagine that 301, everything gets cracked. The equivalent factor is indeed 2, but there is indications from the models that it's close to 2.6. Now, having this in mind, and now going back to the considerations in China, where we have tremendous amount of traffic, you want to overlay a pavement that, for some conditions that are here, I don't want to bore you with that, we got to the conclusion that we needed 14 centimeters of asphalt rubber. I know, this is unthinkable. You never thought about putting 14 centimeters of asphalt rubber. But the alternative would be to put, I don't know, much more, to think that you have to design a pavement for those heavy loads. So then, the concept came that why don't we make new pavements that actually can crack, and they are cheap. Making new pavements with cement-treated bases in China. They have very poor aggregate, so everything is cement-treated. You can go heavy on cement, let them crack. Then, this base is strong because, well, they crack from retraction. Shrinkage cracking, not from, no, this is a strong pavement. The pavement is, resistance is given, strength is given by these layers. And then just consider putting on top whatever it takes, the minimum asphalt rubber combination to resist the crack propagation. And in this case, we consider a SAMI, 6 centimeters, another SAMI, and 5 centimeters gap graded, which you have 13 centimeters actual binder layers, equivalent to 26. Or in another case, where we are on a freeway, we can put the open grade, and in fact, it's like having 33 centimeters of asphalt rubber, but equivalent thickness, but in fact, we have 15.5. So what I'm trying to demonstrate here is by having these materials, SAMIs, gap grades, open grades, that actually what they are really good at, beyond the fact that they are smooth, they have no splash, they save lives. Why don't we think of them as some new material that can be used to control reflective cracking and design new pavements where there's lots of cracks to be reflected here, but we prevent them from reflecting. Therefore, we have fantastic surfaces that, by the way, the pavement structure, the cost of this pavement structure, at least for Chinese conditions, was a fraction of the normal pavement structure they use for the high traffics that is considered. And this is another concept. By the way, the concept of putting the two SAMIs here is make sure that water does not even come to this one, and there is no effect of porous water, pore pressures, and this material is always in a dry condition, and these materials on top can breathe and dry out. So just some other secondary aspects here. So I think that we, over this paper and what you saw today, we can conclude that asphalt rubber can be used to reduce reflective cracking. Asphalt rubbers and SAMIs are not adequately modeled in any of the current design procedures. And we need to think where we're going to go next with our research, because by not using these materials, we're truly bearing more and more money in these roads. And the equivalency factors are actually kind of function how much in strain control a pavement is. I know this is like deep now, but the more in strain control you are, a mix, the better asphalt rubber is. And the equivalency factors can go as high as 10, like in the laboratory reflective cracking that Caltrans done. If you have pavements in those conditions, the overall benefit of having asphalt rubber is enhanced. And now, finally, so new concepts can be considered using these eventually new design methods in which we control the reflective cracking as a new design control. Just want to throw this out to everybody because I get really confused, and I'm sure that everybody that starts learning about this gets confused with all the names in Caltrans, in Texas DOT, and everybody has a name for this. So I think that the gap grade, basically it's, I propose some names like, is asphalt rubber optimized stone mastic asphalt, because out of all the possible SMA gradations, the narrow band of the gap grade that's used in Arizona is like optimized over generations of trial and error. For open grade, I propose the asphalt rubber quiet permeable friction course, because that's what actually it is. And for SAMI, I know SAMI has been around for such a long time that it's difficult to evolve from that name, but in reality, an asphalt rubber, SAMI, is an asphalt rubber bonding impermeable stress-absorbed membrane interface. We kind of forget this bonding because it's very, very tacky and it's impermeable. Because I think it's important to add this to the name to make sure what we're talking about when we talk about these asphalt rubber membranes. So with this, I'm ready to be shut down by all these crazy ideas.
Caltrans limit the thickness of the rubber to be maximum of 60 millimeters. Have you had any experience with a thicker layer in its stability?
I understand that Arizona has done in I-10 up to 75 millimeters. I understand also that the test done at the Arizona State with the confined, the SuperPave, the SuperPave performance test has shown that when used confinement, these mixes are actually very stable. And so I have no reason to believe that they won't be stable even if they use thicker. Now, what people think is that by using more of asphalt rubber may be not cost effective. That's another area. And this is the area that needs to be explored, because the models that they've used so far to make that determination didn't work. So,
Super paver, you mean the terminal blend mix? Is it terminal blend mix, or is just?
That's the test procedure.
test procedure, super pave testing is not talking about. Two over there.
Thank you. I just had a quick question. Are these presentations available on any website for download?
They will be on. They will be videotaped. They are being videotaped, and they will be on CDs, and you can get them from RPA.
Thank you.
More than just that, you have the movie.
Thank you for the nice presentation. I have a quick question. I was wondering if you performed any rotting evaluations, since you mentioned this material is very resistant to reflective cracking and is relatively soft. So I was wondering, if you did any rotting evaluations. Rotting may occur way before fatigue life, since this material is relatively soft.
Okay, there's several ways I can answer that. Better than any test, you just need to go to Arizona and see that the pavements with asphalt rubber have less ruts than conventional material. So the proof is in the pudding. They don't rut. Now, we have done tests, and the tests sometimes, like the Marshall, for instance. If you think Marshall is the test to use, and you test asphalt rubber mixes in the Marshall test, you're going to think they rut, because their flow numbers and everything is lower than conventional. Again, we have to think the models we are using may not be now adapted to the material we have. Let's imagine that someone was trying, just for the sake of argument here, there would be a test in Roman times to test the bending capability of a stone. So they would never use steel, because steel bends and the stone doesn't. So it's ductility. We need to go beyond the traditional test and see, by luck, someone tried these things and it performs well. We need to understand why it performs well. So I'm not concerned with rutting in these mixes, if they're done well. Here? Oh, sorry.
Hi, Pings on MacTech. Just quick comments on the first question asked about the over 60 millimeter. Caltrans did the construction on Highway 33. They have, it's an experimental project. It has included 5 different materials, and they're dry process, wet process, and terminal modified binder process. They have 45 millimeter sections and also 90 millimeter sections. So they did over 60 millimeters. As
Good.
I know that there were no problems with construction. During the construction, they don't have any problems.
Thank you.
You're welcome.
Thank you for putting some stimulating questions out there. I have 2 comments. One is there's a wrinkle that I couldn't include in the presentation this morning on the Federal Highways ALF project, and that is on our pavement models and performance prediction team. Catherine Petros, she's the team leader. She had the forethought to attach to this research a contract with North Carolina State University with Richard Kim. And the idea there is to use rigorous mechanics, rigorous constitutive equations which actually model the damage, where you bring in continuum damage theories and microcracking and other topics of that nature. So I would encourage you to, that is the direction we need to go to, I think, address the shortcomings in what George was saying regarding these models. these. That being said, I would encourage you to contact Federal Highway Administration, the Turner Fairbanks Center, and what we can do is keep you up to date on these advanced models, which is where we need, if we're going to go any further, that's where we need to put our efforts. That being said, last year, no, actually it was 2 years ago at TRB, they put together a workshop, and what it was called was Advanced Models for Practitioners. And they brought in all the researchers in academia, and they did a pretty good program. The idea, and basically they broke it down to say what's important. What is important that you need to know that these models are working on? It's going to be put into a TRB circular, and they also they put it. It was a very late session, so there wasn't very well attended. But I think that document is something that would be good to get to the rest of the folks in terms of advanced models and what they can do. The other comment was I had a good visit from Rod Birdsall. He came to Turner Fairbank, and because I was giving him some background on the asphalt rubber testing we were doing. And now I've kind of living and breathing that ALF study, so I don't really get involved in a lot of characterization for preventive maintenance and reflection cracking, so I'm kind of inadvertently thinking outside the box, and one of the ideas we were kicking around was, well, if you have a certain amount of asphalt rubber you're going to use, well, where are you going to put it in the pavement structure, and what is it going to look like? You want to put it at the top in a mix? You want to put it at the bottom as a mix, or do you want to put it at the bottom as a membrane? And I think you put those questions you put on the weight of advanced models and those types of characterization tests. Forgive me for going on and on.
Thank you very much for your comments.
A lot of the paving projects throughout California, I work in Southern California, are lower TI type projects where you have asphalt thicknesses of 4 or 5 inches, and with a factor of 2 applied to the rubberized asphalt, it almost seems like it makes sense to eliminate the lower AC in some cases. How do you feel about that?
Okay. Now, remember, we cannot forget that we're trying to make a pavement to protect the subgrade. So we need to distribute those loads. When I was trying to present here the concept about these new pavements, where are these? Sorry. I was really considering reducing the thickness of the overlays by making sure that we have a good base, cement-treated base or others. But I want you to also think the performance from the ALF, where you actually had a pavement that was in equal thickness, about the thickness of the pavement you have. You have pavements that you said were about 4 inches, so that's what these pavements are. The asphalt layers is 4 inches. As a new pavement construction, where people right now would say are afraid of putting the top 2 centimeters because it reduces the stiffness, you actually have a much better performance. So we need to control. Very good for bringing that question. I'm glad you bring, because there's a point here that I forgot to bring up. Okay, look here. I just mentioned to you the fatigue. So the fatigue crack on the conventional material was matched by our expectations for fatigue. The model worked well as the model for the permanent deformation in the foundation. Now, please, I forgot to mention this part. Stay on for one more minute. So, you see, this matches pretty much. This is a pavement that would last pretty much the same amount. Now, look what happens in the asphalt rubber section. According to this model, because this is a softer section, this pavement would not survive. This lasted 69,000, 55,000, 66,000. After 66,000, this pavement would be failed by the foundation. This is what our models are telling us. This is the same model you're going to be using to judge the thickness of that overlay. Now, but in reality, we didn't have a foundation problem. We went 300,000 cycles, more than 4 times what this model predicted, and nothing happened. Now, again, are our models correct? This is why I asked them if they had done any IRI tests. So maybe this thing was bumping or what happened, but no, nothing funny happened in this foundation. So truly, I think we need to, your question is very, very good, because you are putting the finger in the wound. How can we reduce this using asphalt rubber and our pavement is going to last? Remember, all our design methods have been calibrated by empirical methods, assuming the performance of a conventional material. But now in these mixes, don't let water go through, if you have a SAMI, for instance. So all our experience with pavements that somehow drip water into that and weaken a little bit the foundation go down the tube. Oh, time is up. Sorry, no more talk.